Okay, hello everyone, my name is Daniel. I will present a general example for shear design. So for the shear design of pre-stressed concrete, so we're gonna cover transverse shear reinforcement, interface shear reinforcement, longitudinal reinforcement, and anchorage zone. So since transverse shear reinforcement is required along the girder, for this part we're just gonna do at the critical section. So the critical section is at a point at dB, is defined as dB, where dB is the distance between the resultants of the tensile and the compressive force. So we're just gonna decide that section. And for this, we're gonna need the DE, which is the distance from the extreme compression fibers to the center of gravity of the pre-stressed steel. So from the figure, we see that it has a height, including the slab thickness, as 80, minus the depth of the pre-stressing tendons, that gives us 64.27. So the second part, I'm sorry. So the second part for this step is to calculate the neutral axis. It was calculated before, but I just want to represent it again. We have 4.68, and since 4.68 is less than 8, is less than the thickness of the slab, we say that it has a rectangular behavior, so that's why this is confirmed. And now dB is, as I said, the distance between the resultants of the tensile and compressive forces, but also it has to be either 0.9 DE or 0.72 H. So we have to take the largest of these three. For this case, it's 62.2 inches. So as shown in this picture, we're gonna design for shear at this section, at the critical section. So we also need to assume that the bearing, the width of the bearing is 1 feet, and this dB is at the center of this bearing. So that gives a total of 5.68 feet from the edge of the girder. So at these sections, from before, you can see we calculated that the shear force at this section is 300 kips. So now the second part for the transverse shear reinforcement is to calculate the component that contributes to the shear on the pre-stressing tendons. So the only ones that contribute to the shear is the drape tendons. So we're only gonna use on this 8 tendons, right? So we calculate the PE, the force in these tendons at 119. We also need to calculate the angle. So to calculate the angle, we're gonna need the eccentricity of only these 4 tendons at the end and at the depressing point at 0.45 L. So that gives us a total of 6 degrees. So then after, we can calculate the BP, and it gives us 20.5. So the third part is the third step is to calculate the contribution for shear resistance. So we use this following equation from Ashton, where the VV is the effective web width and F prime C is in KSI. So ES is the net longitudinal tensile strength in the section at the centroid of the tensile reinforcement. This is based on the modified compression field theory, as we mentioned before. And we're gonna need also the moment at this section, the NU, which is the factorial axial load, the external axial load, which in this case, there is nothing applied in this, so we're gonna take it as 0. And we also need the FPO, which is the modulus of elasticity of the pre-stressing tendons, multiplied by the locked-in difference in strain between the pre-stressing tendons and the surrounding concrete. So that just means it's 70% of FPU. So for the APS, we need to use only the area of tendons that are in the flexural tensile side of the section, that is just from 0.5 H to the bottom part of the section. So that's why we only have 28 tendons in this section. And we multiply by the area of the tendons to get the total area. So here we use the modified field compression theory, and we have two options. So we can go by trial and error to find we assume an angle and then we find beta, or we can also at the bottom you can see that we can also ASHTO allows to use a term use EX as 1, and based on that we can calculate beta and all the other terms. So first, if we're gonna use the trial and error, we just assume an angle. In this case, we did 24 degrees. So based on modified compression field theory, we calculate EX. But since EX is negative, we need to use a correction. So for the correction, it's right here following, and then we get the real EX. So on ASHTO, we have a table B5.2/1, where it shows the different values. If we have, in this case, let's go through it. So we got an EX that is 0.04, which is we're right here, and or beta, or BU over F prime C, which is not here, but we got to be 0.14, right? So the value was 0.14. So we get that our angle is 24.1, which is similar to our trial, and the beta will be 2.78. So those values are correct. So those are the ones that we will be using for the following calculations. So now the next step is to calculate the required shear reinforcement, and we use this equation right here. Note that the angle we just calculated, and alpha is the angle of the stirrups with respect to the plane of the stirrup. For in this example, it will be 90, given that we're going to use vertical stirrups. So given that, we can rearrange to calculate. We can assume the spacing as 12 inches. Then later we need to confirm if 12 inches is valid, and so that we can calculate the area of reinforcement that we need. Is in this step right here. Note that some terms were canceled since they're equal to 1 or 0. So given that, it says that we need 0.3 inches square per feet per linear length of beam. And now we need to check if this value can be used. So we check for minimum transfer reinforcement, and we check for maximum stirrup spacing. So for minimum transfer reinforcement, we have just some quick equations where there is this densified concrete densified modified factor. As for this case, they have many values. For this case, we're using normal weight concrete, and we give that it's allowed that the area of reinforcement is less than this value, and also we check for the maximum stirrup, which there are two conditions. Is either 0.4 dB or 12 inches. So in this case, we have to use 12 inches. So that's why our assumptions are correct. So for the second part, we're gonna calculate the interface shear reinforcement. Again, this needs to be calculated along the beam. And also, so in this example, we're gonna assume that the interface shear, we're just gonna calculate it at the critical section. We're also gonna assume that the surface between the girder and the slab has been roughened to an amplitude of 0.5. And if this is correct, the ASHTO let us check if we need a shear reinforcement, we can waive this assumption. We can waive the shear reinforcement, providing that the transverse reinforcement is extrapolated to the slab. So, which is basically what I'm showing in this picture. The stirrup has been extrapolated to the slab, and now we can check if we need to provide more reinforcement or not. So for that, we calculate the factor interface shear, and we also need the area of concrete that is assumed to be in the shear transfer. So based on these calculations, we we say that the final result is 0.15, and the minimum value is the minimum value is 0.21. So that means that we really don't need to provide more shear transfer shear reinforcement. But still, for this example, we're just gonna continue and calculate the required reinforcement. So first, we need to know what's the minimum interface shear reinforcement. We use the following equation, where ABF is the cross-sectional area of the interface shear crossing the area of the interface. We note that the minimum reinforcement also need not to exceed the lesser of the amount of this amount, 0.035, or the amount to resist 1.33, the shear stress on the interface. So in this case, we're going to assume number 4 bar, 2 legs, number 4. So if you calculate this plus the 2 that we had for the transverse shear reinforcement, we get 0.8 inches. So the next part is to calculate the interface shear resistance, right? And for this, we're gonna need. So for this, we're gonna need the yield strength of reinforcement and a cohesion and friction factor that is given for the type of concrete we're using, right? And PC is the force, the permanent net compression force normal to the shear plane. But note that this force is at the shear, and so therefore, because our neutral axis is above this shear interface, so this force is equal to 0. So that's why here you have it as 0. So we continue. So we calculated before the nominal resistance. Now we need to satisfy another 2 conditions, right? Where the factors K were determined before, that is for the normal weight concrete. So we can see from here, from the calculations, that the PN in the design is 13.86. And if we calculate the total shear resistance, right, which 0.9 is the shear resistance factor for pre-stressed concrete, right, we say that is okay, and the assumptions, all assumptions are correct. And now we're going to calculate the longitudinal shear reinforcement. For this example, we're only going to check at the edge of the bearing, right? In the specifications, it will be required at this section of the girder. So if you had to do a full design, you have to check on along the length of the girder, right? So the forces that contribute to the longitudinal force in these sections will be the applied shear forces, the vertical component of the pre-stressing force, the applied axial force, and the shear force resisted by the transverse reinforcement. Here, this is also, you can, from the modified completion field theory, so this formula, the force required, is based on this assumption. So let's say you have an angle, right? An angle, and if you add the moments about at the point O at the top, then you will, that's the force required for this longitudinal reinforcement. So since we don't have NU and the angle is 0, we can cancel some of these terms, and also at the inside of the edge of the bearing, also this formula applies from the Ashton code. And given this, we can simplify, or we can simplify for VS, right? And we get this 279 kips. And now, since since we have so the force required will be that plus the resistance factor of 0.9, so the answer will be 392 kips. So the force needed to resist, the force required to resist must be supplied by the reinforcement on the flexural tensile side of the member. In this case, the available reinforcement consists of straight strands. So the available force can be provided by this strand at the critical section for shear, but it must be determined that there is a lack of full development due to the proximity of to the end of the girder. So we need to check if this here we need to provide just a mild stirred reinforcement for the longitudinal part, or if the strands are enough to resist these forces. So the available longitudinal force for the straight strands, it's only for the straight strands, it will be the area, these 28 tendons times the FPE. And note that X is the location computed assuming a linear variation in stress from the end of the girder to the transfer length. So since we found that this location is within the transfer length LT, so the available stresses is less than the effective pre-stress force of the straight tendon. The available pre-stress force at X is therefore computed assuming a variation from the end of the girder to the transfer length, and that the transfer length is 60 the diameter of the bar or 30 inches, whatever is bigger. So we find that the force available is 479 and the required is 392. So that means that the straight strands are adequate to resist the required force at this location, and no additional reinforcement is required. If the strands had not been adequate to resist the force, additional mild reinforcement would have been added to provide the remainder of the required force. Also note that we could have also reduced the stirrup spacing, which in return would reduce the required force. And now is a quick look into the anchorage zone reinforcement. So we require that the bursting forces, I mean, when we cut the tendons, this force will burst the concrete apart. So we need to provide some stirrups here, additional stirrups, to make sure that this doesn't happen. So for that, we need the bursting force, which is given in this formula from the ASHTO. But note that this force has to be no less than 4% of the total pre-stressing at transfer. So the total pre-stressing at transfer is 44.6 kips. So if you calculate for the area of a steel, based on this formula, we have that we need to provide 2.23 inches at the end of the support. Yeah, that's it for the shear design example.
Okay, thank you, Daniel. If anyone has any questions, please ask now. If not, we'll go for this session 8. This is optional, but since we have time, we're gonna go ahead. Pong, can you please share your screen?
Let's see, some since we have time, maybe there are questions. Need to give people time to,
Yeah, please unmute yourself, and if you have any question, please.
Yeah, even if there are any questions that you would like to submit online, I mean, or maybe later on by email, we'd be happy to address those. So, yeah, it might, some of the material might be refreshing. I mean, because some of you might remember it, but in any event, if there are any questions on the new, ASHTO, some of the provisions, please let us know. So I asked Pang to prepare a little bit more details about the losses, because these are, are usually they are going to be important, and they were implemented in 2005. However, they have more details, and it has been confusing for some of the designers there, and what to apply, and how to, especially with the elastic gain. So in the class, I usually do a comparison between the old losses and the new losses, and even between ACI also changed their losses. They may, after AASHTO made the losses, they changed, and they made them also more simpler. And we do also a comparison with those losses, So Pang, you want to go ahead and do that?
Yeah, can you see the screen?
Yeah, so I want to introduce Pang Lu. He's also a research associate. He finished his PhD at Rutgers in 2016, I believe, and now he has been with the RIME group for more than 5 years as a research associate. Go ahead, Pang.
Can you see the screen?
Yeah.
Okay. So we're gonna briefly talk about this losses, for the loss of pre-stress. I think, as Dr. Nassif mentioned, AASHTO has been made a lot of change, especially lately, for different kind of losses, especially the refined estimate of losses due to shrinkage, creep, and relaxation. So before we go into that, typically there are two types of losses. The first one is the instantaneously losses due to elastic shortening, or due to friction, due to jacking, at the anchorage set. The second type of losses is long-term losses, because of the shrinkage and the creep of concrete, and also the relaxation of the precision steel. So in this, those slides, we just put some, comparison between the old losses, which is from AASHTO 2004, and AASHTO, the new losses compared to the new losses, which is the up-to-dated AASHTO LFD 2020. So basically, they are saying the same thing as I would mention. There was so we first have the total loss that would be calculated by when you adding up, losses from the elastic shortening or extension of the all-time, application of pre-stresses, and or due to the external loads, right? The second one is, if you look at the table in the right side, so the new code actually some, also here there's another thing I want to explain. We call it long-term, losses due to long-term shrinkage, creep, and concrete relaxation. So the new code provide a estimate, the rough estimate, not the refined estimate of that long-term losses, while the code also provide a refined assessment of each losses due to shrinkage, creep, and relaxation. So when the design they can, really depend on their need. If it's in a preliminary design, they could just use this, estimated losses. When you go to the later stage, you can refine those losses, especially when you have those preliminary design parameter, so you can use those parameter to refine those losses. Jumping, if you guys need, Dr. C, if you need to add something that worthwhile to mention, okay?
Sure.
So we separate them for the pre-tension member and the post-tension members because, naturally they are a different type of pre-stressing. So the code really appreciate these differences and provide different equation for each type. So let's go to the each losses. So first, for the instantaneous losses, actually the old code, new code doesn't change too much. We checked that. And basically, we have two type of equation between the internal pre-stressing tendons and external tendons, right? So I'm not gonna go to, although I put all those, notations here, but in this chapter is really a lot of details For those who are interested, I put the article number here that you could go into the AASHTO LFD to get more knowledge about these equations. So basically, those equations are dependable of the stress in the pre-stressing steel, at jacking, because this is before, instantaneous losses. So you will need that, which at jacking before the transfer. And the second one, you need the friction coefficient, that the unit is per foot of tendon. And also one more important is a friction factor that you need. And AASHTO provide this table, right? In the also you can look at the table 5.9.3.2.2 B1, right? So for different type of steel, Y or strand, high strength bar, you have different type of friction efficient K and the mu, friction factor, right? So basically for the friction losses, the new losses, old loss doesn't differentiate each other. So they're basically similar. So next one is elastic shortening. Similarly, the code doesn't change too much, but the new code has some alternative, like if you look at the equation on the bottom right, it has an alternative equation that you could use to double check your losses, right? So also we are differentiate for the pre-tension members and post-tension members. They are, I think Wasim has covered this part, the elasticity of pre-stressing steel, and also you need the modulus of elasticity of the concrete at the transfer, right? So FCGP is a concrete stress at the center of gravity of pre-stressing tendon due to the pre-stressing forces, right, immediately after the transfer. So these are the instantaneously losses, right? So next one, we go to an important change that AASHTO has made for the new losses is about the time-dependent losses. So at the first tier, which is approximate level, that AASHTO provide approximate estimate of the time-dependent losses, right? The reason why they provided it, because at the beginning of the design phases, you don't have all those preliminary design parameter, how many tendon you're going to use, what's what type of steel, or is it a low relaxation? Hello.
Yeah, go ahead. Yeah, I think.
Like different, you don't know those parameters, so you could use this approximation estimate, of the time dependent losses. So for the old code, which is AASHTO 2004, the equation, right? I mean, this equation was provided in table 5.9.5.3-1, was mainly depend on the partial pre-stress ratio, right? I put the equation here and some notation for you how to calculate this PPR, right? While in the new code, I think after they have done a lot of testing, this is major change they're proposing, and they really consider, they produce, correct this losses with some correction factor, right? For example, to account for the humidity of the ambient air, right? So you have a correction factor for that. And you also have the, correction factor for the concrete strength at the time of transfer, right, of the concrete member. So this equation, you can also go to the new LFD. This is a major change, I would say. So be careful with this. I think they have, use this equation develop this equation based on a lot of testing in the lab, right? So the next one also, so we have shown some approximate estimate of the time-dependent losses, right? So on the second level, which is second tier, the AASHTO also provide you how you can estimate those time-dependent losses more refined, right? Based on, so each factor they have, for example, shrinkage, creep, and relaxation of the pre-stressing steel. Those are the three major things we consider here. So for the old losses, it basically, more depend on the H parameter, right? H is, the average annual ambient relative humidity. While in the new losses, it has more refined, complicated equation due to the space. I didn't put all the notation here, but Yeah, another thing you need to pay attention to is if you look at the losses, there's really a two stages of losses, right, for each of those time-dependent losses. The first stage is the time from your transfer to your DAC placement, right? And the second one is from the time of the DAC placement to the final time, which is when after when this losses has stabilizes, right? So you have to be consider this those two different those losses from two different time periods. And this is, I think, the major changes that the new AASHTO has compared to the old code. Same thing for the creep model, right? The creep losses. The old model, which only provide you with one equation that it depends on the concrete stress at the center of gravity of pre-stressing steel at transfer, and also of the change, depend on the change of concrete stress at center of gravity of pre-stressing steel, due to other permanent loads, right? Such as girder, your DAC, your asphalt, those kind of things. While for the new code, we still separate them, with the two time period, from the time of transfer to time of DAC placement, and time of DAC placement to the final time. So also this is a little bit complicated, which is mainly you have the phi factor, right? Phi B factor. So TD is time of DAC placement, right? And TI is initial, right, at the transfer. And also, we use those two parameters to differentiate this is, between those two time period. So if you're interested, you can go to this chapter, which is, I put it here. I think it's same chapter, as 5.9.3.4, which we the code talk about the creep model, and also there's a good creep coefficient that be careful. This is from the previous chapter, which is 5.4, right? So you got to go back to that chapter. So this is really a lot of parameter we have to consider, but I'm just showing some conceptual thing that you need to know before apply these models. So next one is the relaxation of the pre-stressing steel. Again, this is a major, I think it's a major changes, to simplify it. I think from the old model, this is one thing that we have simplified a little bit, right, from our old, AASHTO code. So same thing, you can go to this, AASHTO, chapter, to look at this, which is same. We have two periods from transfer to DAC placement, and from DAC placement to the final time. And next one is addition that the new code has, to consider, right, about how about the DAC concrete shrinkage, right? So after you place your DAC, your DAC gonna behave, have the shrinkage problem also. So the new code really considered this, put additional model to estimate the refined value of this, shrinkage of DAC concrete. So I put this is equation that you should be looking at it is 5.9.3.4 0.3D2, right? This is equation, and it was like we mentioned before, is mainly depend on the girder creep coefficient, for the two time horizon, right? And also the area of DAC concrete and the eccentricity of the DAC respect to the gross composite section. So pretty much that's it for the comparison of old losses and new losses. Again, I might go a little bit quicker, but I just want to show you guys the conceptual things, because there's so many equation and notation involved in this model. So any question regarding this part?
Yeah, I think, Peng, thank you. I think this is one of the things that right now have not confused, but it's being addressed in the sense that when you estimate the losses, for example, depending the time at which you start putting the deck. So you really need to know that, because then when the deck, if the girder has been on the bridge for, let's say, 1 or 2 months, and then you cast the deck, so the girder has already shrunk, and the shrinkage was applied, but now the deck, which become composite with the girder, is going to start shrinking, and you need to really know what approximately what is the age when the deck has been cast and placed. So those are very much details that designers might not know exactly, but you have to have some estimate what would happen. The other one that I heard that we worked with, because we tried to compare that, was the elastic gain. And in some case, there are 2 approaches. If you use the elastic gain, which is a new concept, but it's really it's correct in a way, is that you what you have taken away, you can bring it back in a way, and sometimes. This was the concept of that was not easy, but for people to comprehend. But I think the losses, the way they're applied, either the shortcut approach or the refined approach, they should give you very similar results. And depending on which one you would use, then you would get if you use the approach with the elastic gain, that means you are calculating the losses more accurately than before, and therefore the live load factor there should be 1.0. So that's the new change that took place after 2014. Was
right.
both and that one. So the losses play an important role, and it depends which method you would use to be able to achieve that. So I think we're approaching 3:30. I think we were supposed to adjourn at 3:50, but surprisingly we finished earlier. So if there are any questions, we'll be happy, or any discussion, we'll be happy to address them. Otherwise, I'll just take a break and ask everybody to if they have any comment they want to make.
Yeah, I think this is the equation you were talking about, right?
Right.
That if you use the refined estimate of the time-dependent losses, you could use 1.0 for survey 3, while for other cases you could use 0.8.
Yeah. Well, if you take advantage of the elastic gain.
Elastic gain, yeah.
Yeah, and then you are getting the estimate to be more exact than before, and thus the load factor has to be more 1. Pretty much both cases have proven 0.8 and 1, the outcome should be the same, but it depends on what losses method you're going to be applying. If it's the refined or you use other approaches, then the load factor has to be different. Okay, and we don't have any more. I mean, we could have added more stuff. I wanted to do the anchorage zones, but I thought the time was too limited. I wanted to stress the basic, so with this, I want to thank everyone involved, especially my colleagues, who were helpful, and they've shown that they have very good command of this precast concrete. We value it a lot. We do a lot of research. By the way, Adi, Daniel, Wasim, they're doing a lot of work in the lab by testing, precast concrete beams, post-tension. Now we are leading the effort to do bonded and unbonded tendons. When you have a combination of both, how do you calculate the stress at ultimate? And how do you find the capacity of both? Because, so we developed some equations. We are validating them. We are also using FRP tendons. And, Daniel is now doing work with FRP tendons, but also with ultra high performance concrete. We were able to mix them and build them in the lab. I think that so far he has about 4 or 5 of them done. So our research is ongoing, and there's a tradition at Rutgers that precast concrete, with Professor now is starting that. We are very active in the community with PCI, with PTI, the Post-Tensioning Institute, and ACI. I used to chair the committee in PTI on bridges. And also I was an ACI, I'm an active member in the Bridge Design Committee and the Technical Activities Committee, which oversees all the technical committees. I spent 6 years on that committee. But I think what we are providing is really state of the art in terms of what the knowledge of the code. We have the inside, deliberation that happened when there's voting on the research behind it for the LRFD. So I hope that was transmitted to you, so that the codes are written by people like you and me, and these are not sacred. Their application should be done very carefully. These are minimum standards, and once you understand them, you aspire to do better in design and safer designs. And I don't want to forget my previous students, alumni, who really contributed a lot in my design courses, especially bridge design courses. And I want to thank Ali, Eric, and Hannah, and Ankur, and everyone at the BRB team from the NJDOT side for bringing this idea together. I think this is great, even for us. It helped us go back and enhance our notes and see what is the most updated. So I like to do this maybe annually, whatever isn't something new, and I look forward to do the steel bridge design in the next one. So thank you again, and I leave the last word for Ali and his team.
Okay, Professor. It's been a long workshop. Hopefully, if anybody has any questions that come up later on, please, ask the professor or Jay Cook, or email them. I'm sure they'll be glad to answer your questions.
Yes.
Now, this workshop was part of the BRP Bridge Resource Program, and I believe the next workshop will be on steel girder bridges. We will try to schedule that sometimes in January of 2022. So that should be an interesting workshop. Again, I want to thank Professor Nassif, Jay Cook, and all the team at Rutgers, at RIME.
Thank you.
And I appreciate this workshop. I think we learned a lot as far as pre-stress and deck. I hope I didn't ask too many silly questions, but but then again, there are no stupid questions, right? So again, I want to thank RIME team, and especially Professor Nassif for his time, and hopefully we'll get to do this again in January.
I hope so. I think the format didn't lend itself to interactive, but I'm hoping in the future, we will be in person, and that will help much better.
Well, I gotta tell you, Professor, the way this variant is going, I don't know what's going to happen, to be honest with you.
Yeah, maybe this would become the norm for a long time.
I don't know. Yes. By the way, I know some universities have gone virtual. Is Rutgers thinking about going virtual?
I think the decision is not yet made. I mean, the university really tried every effort to bring everybody back. I've been teaching in person. Some other colleagues, they opted to do it online. But for the next semester, we don't know what the decision is going to be. So far, it is in person. Mm-hmm. We're following all it's big auditorium. I mean, the students are always with masks on. And the decision, there's a committee that consults with the president, but every time they make a decision like that, I think the impact on the university is really hard. I mean, we're losing money, the dorm, all this, it makes it very inconvenient. And so it's a big burden on the university, So I think they have to make a decision very carefully.
Well, if you hear anything, I would appreciate if you let me know.
Yeah, there is debate now. We'll see. I think with the break, they will probably decide early in the January, because I think ours is in January 19. So they will let people know, depending, and the numbers in New Jersey are spiking a little bit, but not like other locations. Mm-hmm. So they want to monitor, and there hasn't been any input from the state. So I think they wait also for what the the state wants to do also. What is the
DOT? We're all 100% in person. So, we just, I don't know what the governor is planning. So, but on that note, Professor, stay safe.
Thank you.
You and your team and everybody in this workshop, happy and healthy holidays and a prosperous new year.
Thank you.
And again, thank you very much.
Yeah, happy holidays and happy new year to everyone. Thank you all for attending. I know you might have had a burning question. Please send the email like Ali said. We'll be happy to address it. Thank you.
Very good, Professor.
Happy holidays, Professor. Thank you. Take care.
Thank you. Have a good day.